All right, today we're going to talk, or in this lesson, this is what I did not get to in class, we're going to talk about logistic equations. A logistic equation in its general form looks like this. And what the graph looks like, generically speaking, a logistic graph looks like this. Oh, that was not a very good logistic graph. Let's try it again. What happens, and this is a really good model for a population. So let's say deer, for example. Deer population starts out small. You only have a couple deer at the beginning of time. So this is measuring time, and this is measuring, let's just say it's the population of deer. So at the beginning of time, the deer population is pretty low. There are only a few deer, but as they start to reproduce, their numbers grow exponentially. So right about this point, they're growing the fastest. And then it comes a point where they could continue to reproduce through time, but their surrounding area, the predators around them, the food sources around them can only support so many deer. So it comes a point where this graph starts to level out. So we would say that the limit as t approaches infinity, so in other words, as time goes by, there is a limit to the number of deer that could fit in this, or that can survive in one area. And we call that value, that's the L value. So if you look at the equation, the general equation of the logistic equation, that numerator is the limit. We call that the carrying capacity. So now let's talk about the derivative of this. That carrying capacity is a big deal, and that's basically mostly what you're going to be asked on the AP exam is about to find that carrying capacity. So if we look at the derivative, and you can spend the time figuring out where this derivative comes from, but if we differentiate that with respect to time, we end up with this equation. K times y times the quantity 1 minus y over L. It's hard to talk and say that at the same time. So if you'll notice in this derivative, the carrying capacity shows up here as well. So on a multiple choice question on the AP exam, the question might say, given this derivative, they would want you to find the limit as t approaches infinity for y. So in other words, they're asking to find the carrying capacity. So you don't need to actually find the antiderivative of this derivative to find the original equation. If we can just rearrange this derivative equation to be more in this general form, then we can find L pretty easily. We can find that carrying capacity. So let's do that. I know I can see that in this general form, I need to make sure that it's, something is being distributed out and that it's 1 minus a fraction. So in order to make that happen, I need to make this first term become a 1. And to do that, I'm going to factor out 3y over 20. 3y over 20, and I factor out 3y over 20, that leaves me with 1. Now comes the fun part. If I factor 3y over 20 out of y squared over 1600, what's left? Okay, so let's do that here on the side. So if I've got y squared over 1600, and I'm dividing out the 3y over 20. And I'm dividing it out because if I were to distribute it back in, it would be multiplication. Okay, so we're going to say y squared over 1600 times 20 over 3y. If I combine those two together, I get 20y squared over 4800y. The y's will reduce, so I've got just one y left on the top. 20 over 4800 reduces to 240. So I can now put this back in here. I can say that y over 240. I can now find the limit because I know the carrying capacity. So if I were to have the original equation, the limit as t approaches infinity, the carrying capacity is 240. Okay, what if the question asked you to actually write the original equation? Okay, so if I asked you to find y, that's a different story. So we're going to use the exact same equation. So given dy over dt find y, or solve the differential equation. So we already did a little bit of the work. We've got dy over dt equals 3y over 20, or let me write it even more different than that, 3 over 20 times y, and then I've got 1 minus y over 240. So I just learned a lot from this equation, because that general form of the derivative of a logistic looks like this. So I can find k from this equation, and I can find L. I'd also have to tell you a little bit more information. So find y if at time t equals 0, the population is 15. All right, so we know a lot of information now. We know the k value is 3 over 20. We know the value of L is 240. So let's plug in the things we do know. Y equals, we know 240 is the carrying capacity. 1 plus b e to the negative. We know k is 3/20 times t. If we can just find the value of b now, we can write the equation for y. No need to find the antiderivative. We have all of these parts, and since they gave us this initial condition that when time is 0, the population is 15, we can find b. So let's do that. Population is 15. And then time is 0. E to the negative 3/20 times 0 is e to the 0, and e to the 0 is 1. So we end up with 240 over 1 plus b. I'm trying to solve b, so if I multiply 1 plus b over to the other side of the equation, I get 15 plus 15b equals 240. And I know that 15b is 225, so b is 15. All right, now I have enough information. I can write the logistic equation for this information, for this differential equation. So I have 240 is my carrying capacity. I just found b to be 15, and this is negative 3/20 times t. Now I can find the population at any given time. So really, I hate to say this, but my recommendation is that you memorize these two formulas, that you know the general equation of a logistic and you know its derivative. That's going to just make your life easier. If you have to create this every time, it's just going to take too long. And the bummer part is that you might see one question on it, but it's nice to get that one question right. Okay, that's it.